Right, segment routing is an advanced MPLS traffic engineering. See, for MPLS traffic engineering, you don't need RSVP to do traffic engineering if you are doing segment routing. In normal classical MPLS traffic engineering, for signaling you need RSVP. That's an additional VP. It's an additional protocol, which is no more needed. And also, for distributing labels, when you enable MPLS, LDP gets enabled. That is also no more needed. See, I'm trying to explain you why segment routing. Segment routing reduces the number of protocols that you overload. In normal MPLS, you cannot do label switching without LDP or TDP. LDP is industry standard, TDP is Cisco. Whatever. You need a distribution protocol. Without that, it won't work. Which is an additional layer of protocol. On top of MPLS, you run LDP. And if you want to do traffic engineering, you enable RSVP. That is again another protocol you are adding. So complexity is becoming more and more complex. Segment routing makes it simple. Not too many protocols. You can do MPLS label switching without LDP. You can do traffic engineering without RSVP. Isn't it simplified? Of course it is simplified. It reduces the complexity. It is simplified. Segment routing is less burden to the routers. Not only that, for the developers who develop some software for automation of work, networking job, for them also it is easy. If you don't have too much protocol, then less encapsulation. Less encapsulation is what the developers look for. So segment routing, what it is, we just saw a little bit of why segment routing, but we did not see what is segment routing. Why segment routing? Reduces complexity. Without MPLS, with MPLS, without LDP and RSVP, I can do label switching and traffic engineering. That's one of the biggest reasons why segment routing. Now, what is segment routing? Segment routing is same like traffic engineering in MPLS. Based on the source, the path is determined in traffic engineering, not based on where you go, based on from where you come. You will be placed into a tunnel and a path is going to be determined. That is traffic engineering. Almost same explanation we give for segment routing. Segment routing is a method of forwarding packets based on source routing. Meaning, when the packet enters the PE1, when the packet enters the PE1 router, when the packet enters the PE1 router, the path is going to be determined. You may be having multiple paths. As it enters, this router knows that this is the path via which the packet is going to go. It knows very clearly It knows the source router, the source PE knows very clearly the path. Now, what is the difference between segment routing and traffic engineering? Traffic engineering is also source-based routing, based on source routing. Now, what is the difference? There is a very big difference. What is it? The path order list is encoded into the packet header. The path order list, meaning what? Path order list. Let's see. Let us say there are some routers in all the three paths. And if this is the path that is going to be given, the order list, meaning the information about this router, this router, this router, and this router will be informed to the packet right here itself. The packet will know, I'm going to meet Robert. I'm going to meet James. I'm going to meet Ram. I'm going to meet Grish. It knows. Right here in PE itself, the packet knows that I'm going to meet Robert, James, Ram, Girish. It knows very well the list of routers which is going to be there in the path. The nodes that are going to be in the path. And this forms a segment. And these routers are lists, segment lists. List. Ordered list of segments. Each node is a segment. You see, segment routing. The router here knows the segments via which the packet is going to go. Method of forwarding the packet based on source routing, where the routing path is encoded, means embedded, means added, meaning inserted in the in the packet header. And those routers in the path, each router is one segment or one node. All those routers information in the path is what called as list. And also it is in order. Who comes first, who comes next, which router comes next, which comes last. Very clearly the order list of segments. See, it's a very nice thing. Right in the ingress router, the packet very clearly has got a picture of how I am going. This means that traffic can be forwarded selecting any routing path, not just the IGP given shortest path. Same like traffic engineering. Any routing path, any path that is available. It is not saying any path available in the routing table. It says any path that is available. It need not to be there in the routing table. It need not to be a shortest path. Any path, any routing path can be used. That is what we call as traffic engineering. Traffic engineering is you decide how the packet should flow. Engineered. Segment routing is an ingress routing. You can also say, instead of source routing, you can also say ingress routing. Why? As the traffic enters the ingress router, the MPLS labels that are going to be used to reach the end of the other tunnel, end of this tunnel, the other end of the tunnel, is being encoded. Again, I want to tell you, segment routing uses MPLS label. But in IPv6, you don't need even this MPLS. Wow. You don't need even MPLS to do segment routing. In IPv4 segment routing, when you capture a packet, you will see a MPLS layer that will have this ordered list of segments. Whereas when you capture an IPv6 segment routing header, packet header will not have MPLS. No MPLS is needed if you are doing IPv6 segment routing. For IPv4 segment routing, we need MPLS. For IPv4 segment routing, we need MPLS. Do we need LDP? Anyone can answer. Do we need LDP?
No.
No, sir.
No. But for IPv6 segment routing, you don't need even MPLS. The IPv6 header itself have got an extension where the label, if I say label, you should not immediately think, without MPLS, how you got label? Okay, so there is another word, segment ID. Label or segment ID both are same. In segment routing, we call it a segment ID. In MPLS world, we call it as labels. Both are same. So in IPv6 header, the labels are going to be there in the IPv6 header itself. Which is also called a segment IDs. Okay, so segment routing is the ingress routing using MPLS labels. If it is IPv6 segment IDs, for IPv6 you don't need separate layer for the label for the segment ID. In IPv6 layer 3 header itself, you will have the ID. Okay, anyway, we are not going to focus on IPv6 SR. We are going to simply focus on IPv4 SR, which is MPLS based. We're not going to focus on SRv6. But I tell you, SRv6 is much more easier than SRv4 or MPLS based. Now, let me go to the next one. Labels are stacked at the source. Labels are stacked at the source. I told you, as the packet enters the ingress router, all the labels in the path, all the labels that is needed for the path is arranged, it's stacked one above the other inside the packet. Meaning of each label is one destination. So if MPLS is not going to, sorry, if MPLS labels are needed for segment routing, if you need to stack the list of labels in the ingress router, you need the labels of other routers, right? You need to know what label the other guy is using if you want to stack it and give it in the ingress. Now, who is going to distribute it? You're not going to use LDP. The label distribution protocol, if you're not going to use, then who is going to distribute? Anyway, we have to use a routing protocol. We will be using one like ISIS or OSPF. This itself can be extended. OSPF LSA types or ISIS TLV type length value. itself is more than sufficient to distribute the MPLS or the labels. You see, anyway, OSPF and ISIS, they are going to send hello packets every 10 seconds. The OSPF sends the hello packet, ISIS sends the hello packet, OSPF sends the updates, type 2, type 3, type 4, type 5, type. You have a lot of LSA types. Up to type 11 you have 9 to 11 opaculus. So now this OSPF or ISIS TLVs and LSAs can be extended to carry the SIDs of each link. You see? Now you understand why we do not want to use LDP, why we no need an LDP. We have OSPF, we have ISIS, which is already talking to every router. They themselves can distribute it. Why segment routing? I just started this class by telling why segment routing. In that I gave you two reasons. You no need LDP and you no need RSVP. But I'm not saying if you want LDP for normal MPLS, you say for example on one router you want to run both MPLS and segment routing. Then it can exist, no problem. It can coexist. But for simple segment routing alone, you no need LDP. Segment routing is the latest technology that replaces MPLS and is based on the source routing. Segment routing provides complete control over the forwarding path. Path, very important. From the source node by encoding the path in the header of the packet itself. Segment routing is implemented using extension of the native OSPF and ISIS routing protocol. So it does not require any additional LDP or RSVP protocol. This removes unnecessary protocols, thus simplifying the network. As we already saw, segment routing can run natively on an MPLS, or it can use IPv6 header and can coexist with LDP. If you want to do migration from MPLS to segment routing, you can have both, and once everything is smooth with segment routing, you can remove LDP. So you can coexist. Already you are running MPLS LDP. And if someone is saying we need to migrate to segment routing, if those devices are already supporting it, you can easily migrate without disturbing the traffic. Enable segment routing, verify everything is fine, decommission LDP, finish. No disturbance to the traffic. Painless migration. Yeah.
So you said the ISIS or OSPF.
No other protocols can be used because they are not link state protocol. They don't have complete topology info. Only ISIS and OSPF advertises the link state advertisement. Only this can have the complete database of the topology. Because segment routing can use any path, even that is not in the routing table, you need a database of complete
Topology. Okay.
topology. You know, we just saw it can be any path. It can use any path. So you need complete topology. Only ISIS and OSPF have got that. Why segment routing again? Segment routing, viewed widely as next generation of MPLS, makes the network more scalable. I just told you how it is scalable because you have reduced the complexity of the network by reducing the protocols. You have reduced the complexity of the network by reducing the protocol. Instead of encapsulating, just change from the ground level. Scalable and intelligent while improving the capacity utilization, leading only low cost, greater user satisfaction. So it leverages the source routing by providing simple, stateless mechanism to program the path, packet that goes through the network. So when I say program, what I mean is the stack of list of segment in the path has been added to the header. Not only that, when you develop a software to automate, it is easy for the developers to develop, as I said earlier. If it depends on many number of protocols, then the developers first of all need to do CCNP, CCIE, which they are not ready because they say we are programmers, man. Why we need to study? Then how we are going to develop a tool for which you do not know? So if you give just one OSPF, you need to know to develop a software. Only ISIS you need to know. Everyone knows ISIS and OSPF because it uses binary tree algorithm. Right, in college days you learned it. SPF algorithm. So it enables granular traffic control without need of additional protocols like MPLS-TE. In addition, it does not require any path signaling like LDP. This makes high scalability. There is no need for signaling because you are going to have the stack of labels which is needed for the path. You don't need anyone to say, come to me, come to me, come to me, I'll take you, come to me. This is the label, use this, come to me. No need of that signaling. What does that mean for me? Segment routing simplifies the network by removing the protocols and automating the operations. Granular traffic control allows you to achieve high level of bandwidth utilization without impacting resilience. Network resilience is achieved with 50 millisecond restoration of connectivity. So this is an acceptable one. Convergence time, 50 milliseconds. Because it's not complex. See, normally when you do normal RSVP traffic engineering, if you shut down a path and say no shutdown, shut and no shut, it take a long time for the path to get activated for RSVP. Why you know? First OSPF should come up and then MPLS LDP should come up. After LDP get converts, then RSVP should come up. Once RSVP signaling everything will go over, then only the tunnel get established. See how long it takes. Because you have too many protocols, one depends on the other one. The first one should get over processing to make other next protocol to start processing, and second protocol finishes processing, the third protocol begins. Only when third protocol finishes, you are able to see the result. The restoration of connectivity takes a long time if you have too many protocols. So, segment routing value propagation. What is the best? Why do I need segment routing? What is the best out of segment routing? Control plane simplicity. No LDP, no RSVP. Just use IGP itself to allocate and distribute labels. Topology independent loop free alternate. What is this? Topology independent loop free alternate. When there is a break in the path, when a path breaks, you can immediately swap to the alternate path, a loop free alternate path, without waiting for the topology to say, hey, you have a backup path, come. You have a feasible successor, come. No need. You no need to wait for the topology to provide you a backup path when the primary goes down. You already know it. If this primary goes down, what needs to be the backup? You already know it. So fast rerouting is possible. Topology independent, loop free, alternate. Segment routing takes the link state. That's why we need to use only ISIS or OSPF. So what segment routing does is it copies the link state IGP topology from the topology database, divides it into subpaths called segments. So it says, okay, for that destination, there are 3 paths, which means there are 3 lists of segments. Fine. So to identify that segments, there are 4 different segment IDs. In segment routing, there are 4 type of IDs. We are going to see in the next page. Very important. 4 main segment IDs. Let me ask you a question before I move further. In MPLS layer 3 VPN, MPLS layer 3 VPN, for a customer traffic to go from left to right, traversing through the ISP network, what are all IDs you used? You used a destination IP. For that, you used the MPLS label for transport. You used another MPLS label for VPN, which is called as service label. And then you use the route target. And then you also use route distinguisher. You see how many IDs you used? Route distinguisher, route target, VPN label, and then local switch label, and then the destination IP. Isn't it? You use a lot of identifier to go to some destination. In segment routing, we have 4 main segment identifier, which we'll be seeing in coming slide. Why do I talk about MPLS layer 3 VPN? I want you to compare. I want you to think and realize how segment routing makes things simpler. There, without route target, you cannot do. Here you can do. There, for MPLS VPN, you need 2 layers of MPLS. Here you don't need. So if you don't need, then something is replacing to fulfill the necessity. So you need to expect that what is added in segment routing, which is not there in MPLS layer 3 VPN, that fulfills, that solves. So there are four main segment identifier. We'll see in the next page. Next, link-state IGP TLVs are used to encode various segment identifiers. So who is distributing the IDs, those four IDs? For every network, there is four different IDs. Do we need BGP? No. You see how simplified it is. For route target to get distributed, you need extended community BGP. Here, the link-state IGP TLVs are more than enough to encode various segment identifiers. What are the segment identifiers? Prefix segment ID, node segment ID, adjacency segment ID, binding segment ID. What is prefix segment ID? This is the ID that is given to the loop back address on each router. Global significant carries label information required to reach a specific prefix. I'm sorry. This one that I wrote is for node SID. Loopback address on each router identifies that router, isn't it? Why do we use the router ID as loopback 0? Because we want to identify the router as loopback 0's address. We usually in OSPF or ISIS or BGP or not ISIS, OSPF or BGP, it uses router ID, no? It uses which address? Loopback address. That loopback address, loopback interface address is what the ID of that router, even MPLS. So the router ID is what we call here as node SID. See, their router ID is 32-bit. Here it is not 32-bit. Yep. So we need ID for identifying each router. For that we have node SID. And if you take the node SID or prefix SID, any ID you take, it will be only between the number 16,000 it will be in between this 16,000 to 23,099. This is the range called as segment routing or global block. Segment routing global block is only between these two range, 16,000 to 23,099 global block. Now, what is the difference between prefix SID and node SID? Node SID represents node. It is assigned to the loopback address. In our configuration, you will see this. In our configurations, you will see this. I'll be configuring SID under the loopback. For example, if I give SID 40 to one of the router, you know what will be the, if I give prefix ID under the loopback as 40, you know what will be the node ID? 16,040. You understood how you got 16,040? It is this number plus the ID that you assign to the loopback as node ID. I want you to understand this. You are not going to give 16,040 as the node ID under the loopback interface. But there is an option to give absolute value like this, but not necessary. You just simply give 40. It will take it as 40 plus 16,000 automatically. You no need to give the absolute value. So that is node ID. Then what is prefix ID? In that node, you may have many networks. For each network, there is an ID which is globally significant, which is unique across the entire topology. For every specific, we call it as prefix SID. Hope you understood prefix SID. Prefix SID is the unique segment identifier, which is global, unique for every single network. Node SID is the one which helps to identify globally a router, a node, a segment, a router, because the loopback address is what we usually use to identify a device, a node. We'll use the SIG ID that we manually give to the loopback interface as the node ID. I want to tell you something here. For this only you will give SID manually under the loopback. All the prefix IDs will be dynamically generated. You no need to worry. Don't care about it. But here you need to carry one info. What is that? Node ID I configure. Prefix ID is, though they are dynamically generated, they are going to be unique. Because based on the node ID, every prefix in that node, the prefix SID will be generated, so there won't be any conflict with the other nodes. There is something called adjacency ID. Adjacency ID is same like IPv6 link local address. The link local address, how many you have for a link? You have two, right? You have two adjacency ID for each link. That is to identify the link only. Each link will have two adjacent SID. And this is locally significant. Here, the adjacent SIG ID, here the adjacent SIG ID can be same. It don't conflict. Locally significant, non-unique, can overlap across the entire topology, used to identify just the link. On one router, you should not have same address ID. Here it should be different, here it should be different, here it should be different, here it should be different. But here you can have, if here it is 1, 2, 3, here also you can use 1, 2, 3. No problem. But on the same, it cannot be 1, 2, 3. This should be unique, this should be unique. It's locally significant. Same rule for link local ID in IPv6. Binding SIG ID used for interworking, means for SRTE domains and other non-SR domain, meaning interworking means what? You have SRTE, a big network, half of the network is SRTE, other half is RSVP. But this is your network, right from here, alpha to beta is your network. But the problem is in here, the administrator has not enabled SR. Maybe those devices don't support. They do support only RSVP-TE. Here the administrator enabled SR. Can they work together? Yes. That compatibility is given by binding SIG ID. So it will translate SRTE to RSVPTE and vice versa. That is why it is called as binding TE. Interworking, facilitate communication between blah 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 blah. SRTE and RSVPTE. You don't need to worry about these, I tell you. Just focus only on this. That's what you're going to configure. All other things are automatic, taken care. So segment identifiers are prefix SID, node SID, adjacent SID, binding SID. Prefix SID is the globally significant unique SIDs given to prefixes. Node SID is also again globally significant unique SID given to the loopback interface address of a router that represents a node. Adjacent SID is to identify a link. For each link, there will be two adjacent SID for each end. For this end and that end needs ID. Binding SID is needed is there only when you have RSVP and SRTE in one big autonomous system. To provide you compatibility between non-SR and SR domains, we use binding SID. Handling failures, meaning if there is a router failing, a link failing, how the SR handles. As we saw earlier, topology independent loop-free alternate is used to provide fast rerouting around the failures. I'll explain you with a diagram. You see here, the actual path is between A to D is this. This is the actual path. So when the packet enters, this is the stack of label that is added. 10 is given by B, 11 is given by C, 12 is given by D. So 10, 11, 12, this one adds. And the packet goes to B. B will check 10 and it knows that the packet needs to go to D. So it removes the 10 and send only 11 and 12. 11 is what given by C. When C receives 11, it understands to what destination the packet should go. It removes 11 and send the packet only with 12 to D. And D receives the packet. You see how the packet, as it moves from one hop to another, the label from the upper stack gets removed. You see, it pops off. The top label pops off as it goes from one hop to another. Now, if there is a failure in this link or this router, what will happen? This guy will know because IGP protocol is very fast now, OSPF. It intimates, boom, hey, the link failure. See, earlier OSPF will inform and then MPS will come to know, NPLS will remove the label and then RSVP will come to know. It is going to take a long time for conversion. Now here it is only one protocol, OSPF, which is responsible for the label distribution. So immediately B knows that I need to push via this path. So it is now going to keep the last label because that's the final destination without removing that. It just puts this label given by G and given by C and sends to G. G after receiving pops 15 and sends to C. C pops 14 and again back to basis. 12 goes to D. You see? Loop-free alternate. This is what called as loop-free alternate. Is your OSPF loop-free routing protocol? Of course. So the same loop-free is used here, and it can provide you loop-free alternate fast rerouting. And it is topology independent loop-free alternate because you are not waiting for anyone to signal and then discover an other alternate path. You just make use of the database which is already there. That is topology independent. You are not dependent on your topology when a failure occurs. You can do fast rerouting around the failure. Segment routing paths are used as repair tunnels. So automatically, those things are taken care. Path will be via a new tunnel will be via a new path. Traffic engineer, topology independent. So topology independent loop-free alternate does not require a repairing router to be adjacent. It need not be an adjacent router, repairing router, meaning even some router which is in the far, like, where is the picture? See, there is a link failure. Let's say here, there is another router. I should not say C fails. If C fails, you cannot go to D. The link is failed here, not here. It need not to be an adjacent device, the repair one. Even if it breaks here, the path need to be this way, isn't it? That's what here they mean here. The topology dependent loop-free alternate does not require a repairing a router to be an adjacent. It can be even in a remote PLR, point of local repair. It need not to be a local router. A repair tunnel does not have to follow least cost path. Again, the main aim is not a low cost path. IGP will provide you low cost path. The main aim of SRTE, traffic engineering, segment routing, or any traffic engineering is not, they are not focused on low cost. They are focused on providing guaranteed constraint based path. So remote loop free alternate, it will use RLFA, meaning I want to go here. What are the other alternative if this fails? Based on that, okay, I decide this way. This is another path I see in the database. Now, what is the label given by this path? Put that label and send the packet. So this guy inserts new stack of label. Sorry. So solves loop-free alternate or remote loop-free alternate shortcomings. Hence, full link and node protection can be achieved in most network topology. This is the key drive operators developing SR. So this is the main reason for SR. Now, steering the traffic through the tunnel, if you would have noticed me doing this MPLS RSVPTE, I was using static route to push the traffic through the tunnel. That is one way. Another way is auto route announce. What is auto route announce? Even in not only in SRTE, even in MPLS TE, auto route announce is there. Please, I want to repeat again. Even in MPLS TE, I did not do that in the lab. It is very easy. One command I need to add under the tunnel interface. MPLS tunnel auto route announced. That's all. If you put that command, what happens? It automatically writes a route into the routing table for the traffic to go. So your static route is one thing. If you don't want static route, you can inform MPLS TE to write a route for destinations into the routing table so that the packet can go through the tunnel. Or you can write class map, policy map, and you can do policy based routing. If this is the source, if this is the destination, use this next hop address. Something like that. Fine. How does segment routing works? First, you need a routing protocol which supports segment routing. In another word, go under ISIS and enable segment routing. It is very simple command actually. Go under segment router ISIS or router OSPF and you put one line command. How many line command? One line command. That much you need to type. What is the command you know? Segment hyphen routing space MPLS. That's all. That big command you should type. Segment hyphen routing space MPLS. You need to write that command. The truth is, if you know ISIS, enable ISIS first and add only one command, one line command. Segment hyphen routing MPLS. Your segment routing is enabled. Second, as I told you, you need to go under the loopback interface of the device and provide the prefix ID, prefix SID. For router 1, I'll go under the loopback interface and say SID as 1. If I say SID as 1, what will be the actual node SID? Isn't it? 16,001. Don't forget. 16,000 plus whatever you mentioned. You can also use the keyword absolute and type this one, your wish. I have seen mostly people typing only this. Very few people will say absolute value, 16,000, your wish. Both are available. So each node advertises one prefix SID, which is also node SID. And then segment routing global block, I told you earlier, 16,000 to 23099. If you want to go and customize it, you can customize it. Like if we used to give MPLS label range, you can also change that. So every router is going to advertise using the IGP extension header that this is my prefix SID. This is the global block of my router. And two adjacent SID per IGP adjacency. For every ISIS neighbor, to identify the link has got two endpoints, so two adjacent SIDs. SIDs are actually MPLS labels, and the sequence, the order is what called as instruction. Source node only encodes the path in the ordered list, which is called instruction
No, sir.
of the
No, sir.
segment. Any question?
I'll have to go through this video once again and then understand more.
Okay. Okay. Now here is a picture, you see. We will build something like this. we'll have two customer edge. It can be any iOS router. And this segment routing can be done in both XE and XR. XR is little heavy. So you can do one side SR, one SR and all other XE. Because XR, if you take each XR consumes 16 GB RAM. Yesterday, our Girish put in our EV. I put the lower version of
Yes,
it.
sir.
Even that lower version takes 8 GB of RAM. Whereas XE is 4 GB only. Am I right? Am I correct? So, if you want, you can have only XE. Or if you say, I do not know how XR command works, I want to do on XR, you can do that. But I tell you, definitely there is some change in the command, difference in the command. It's not same. XR command and XE commands are not, commands look similar, but the modes are not same. But if you know very well in XE, by simply seeing the document configuration guide of XR, you will understand. You don't need to do and verify that. If you know the story, why we put this command, then you will understand easily when you see the configuration command. Anyway, we are going to do only with XE today. We are going to take 1, 2, 3, 4, 5 XE router and just 2 iOS router. All right, we can also make bigger topologies, but like this, but I do not want to kill the processor. Here we have 10 routers. Plus you also need to add the customer iOS routers. So if each router takes 4 GB, 40 GB for 10 router. No need. Just take simple 5XE and 2 iOS. Okay, but for explaining you things, I would like to have this bigger topology. What is this 1, 2, 3, 9, 5, That is what SID that I am assigning on each router's loop back interface. So what will be the absolute SID of router 10? Can anyone say? 16,010. What is the SID on router 5? Why I'm repeating these things? Because the next page that I'm going to show you will
Yes,
have
sir.
this
Yes,
type
sir.
of output. If I didn't mention now, you will not understand there. Is there any question? Is there any question? Now see. Same topology I have kept here down. And you see on router 10, this is router 10, you know this is router 10. On router 10, if you see the SIDs of router 1 is 16,001. Of router 9 is 16,009. Because I am showing this output on router 10, it won't show you the IP address on loopback 1, it shows the interface itself. It is actually 10.10.10.1/32. Yeah, and the SID on that router 10 is 16,010. So I can see the entire label table on every router. See, the label that is given for this router is going to be same. That is why we learned unique across topology. This is also unique across topology, globally significant. It is not like MPLS. They don't change labels hop by hop. Whatever the label given for this loopback is only unique for this guy. No one will be using it. Every router knows 16,008 means this router. This router knows 16,008. I need to go like this. It's like a router ID. In an area, the router ID of OSPF area is unique, right? It's very important. It should be unique. This is like a router ID, node SID. You see, in router 1, the loopback address is 1.1.1.1. You see the SID configured is 1. This is the information that OSPF or ISIS is going to distribute. For router 7, you see, SID is 7. But what do you learn on the other router? You don't learn 7, you learn 16,007. See, in router 2, when you check the routing table for 7.7.7.1, which is router 7, it shows that this is the label to reach 7. Where are you seeing? You are seeing on router 2. Router 2 says the label for this router is 16,007. For this one, every hop, the label will be same. It's not like normal MPLS. In normal MPLS, every router will have different label, and they swap the label. Here, uniquely maintained. All right, 16,007 is the label, but you just configured 7 under the loopback. And when you see if the router is running SR, you will see labeled SR. It's a normal routing table. You see, I'm showing you normal routing table. Show route and detail I type. Usually you will see all these things, but you will not see this. But you are seeing here because you are having XR, labeled XR. So this is an output on router 4. Router 4 is here. A normal forwarding table. This is a normal command in MPLS we used to use. Show MPLS forwarding table for particular label. It says if you want to go to that 7, you need to go to 5. Is it true? Yeah, you need to go to 5 in order to go to 7. That is true. See, it's the same label. You don't need to have different. You don't have different label to swap. It's the same label you are going to swap. Is this clear? Do you understood? Did you understand how these IDs work and how the outputs can be read? Do you understand any of? You didn't understand any of this? Okay, you understand. You see, even it shows index ID, SR prefix, index ID 7. All right.
Yeah.
So that's about the theory. So the basic configuration, I'm going to make a folder, save this configuration later. I'll give it to you. On C router, let me save this 11.1.11 255.255.255.0 router ISIS. I'll give a process ID called what we are doing, SR lab, some name. Net ID 49 is for private dot. Area ID is 0. System ID is also 1. Area, okay, 1. And then N selector should be always 00 for IP. And I do not want type 2, I just want to have flat type 1, IS type level 1. And then there is nothing more actually. That's it. And I need to go to the interfaces now. Interface loopback 0 range loopback 0 comma f0/0 IP router ISIS SR-lab, and if possible make it as point to point because we don't have multi-point environment. I'll go under the interface, figure out the network type command. Customer 1. Okay, let's give the host name also. Host name CE1. Okay, I can see there's an error here. Interface range loopback 0 comma fast. Okay, leave. We'll do separate. Interface loopback 0 ISIS this. Interface fast Ethernet 0/0 IP router ISIS SR-lab. And I also want to say the network type. I need to figure out the command. I think IS network. Yeah, point to point. Boom. Not mandatory, but I like to because there is no need of DR election. What else? Exit. Exit. So let me paste these things in a notepad. Here I gave this command ISIS network point to point. This is done. Now the next file is CE2. I'm going to do CE2 now.
No, sir, the IP address will be, yeah.
And
22.
yeah, 10.22.22.5.22. And then SR, this is going to be 22 here. Oh, I should have said 11 there. I made a mistake. Anyway, I'll say 22 here. And what else? That's all. I'll save this and then I'll open first one. Okay, before that I'll paste this on second one. And then the first one, I would like to change this as 11. You must not
we will have to
change when
give no
defining
and then
additional area address. I'll do one thing. Correct. Okay. So now let us remove that no in the notepad. I don't want anyone of you to get confused. Let me say this. Fine. So customer side, there is nothing more to do. Let's start CSR side. I'll call it as PE1 CSR1. And in that, loopback will be 1. And there is gig Ethernet 11.1.1. There's another gig Ethernet 2.1.2.1. And then this will be 1. And then this will be G. That's all. This will work. See, same command only in iOS and XI. Sorry, XE. Let's change the host name. PE1. These are all not errors. These are all the logs from this device. Okay, did I save PE1 here? Let me save it.
5.
Next is, let's do CSR. 5 or 2, both have got 3 interfaces. Let's finish 2. Yeah. P router, CSR2. And this is going to be .2 here. And G1 is going to be 1.2.2 here. And G2 is going to be 2.2.3.2. And G3 is 10.2.4.2. And then we need to add another interface here.
NetID should be
Net ID should be 2. This is G3. Save. Okay, so 3 interface G1, G2, G3. G3 is under 4. G1 is under 2. G2 is under 3. This is on CSR2. Oh no, there's a memory issue. Crash. This is very worst. Wow, it's recovering. Yeah. So G1, is this correct? Yes.
Yes,
And this will
the
be 3
IV
here.
3, yeah.
And how many interface we got?
Two interfaces, G1 and G2.
This can be removed. This is for 3. Good. So just one more order. I should save this as 4. And put 4 here. Put 4 here. And G2 as 4.5.4. G1 as 2.4.4. And this will be 4. And other things are okay. Same.
Same, yeah.
This is on 4. Good. Looks like all other things are good. Now I'm going to on this. Let's see. Meanwhile, I'll go and configure the SR commands. All right. So on PU1,
Okay, sir.
as I said, very simple. Router, ISIS, and what is the name of ISIS? Like do show run section router. When it is case
SR
sensitive, I need
hyphen
the
lab.
exact name. Okay, router ISIS SR-lab lowercase. And then I have to say segment routing MPLS. Okay, I have to enable it globally first. Before that, I also need to say metric style wide. Only then that labels can be distributed. It should be wide metric. Very important. So let me note it. Take a note. Right? Did I say it before? Yes. SR ISIS config. In here, I remove all this. These things not needed now. I need to say metric style wide. And before that, in the global configuration mode, segment MPLS IP MPLS segment routing MPLS. That's it. I have to enable this command.
Feature.
Now go back to ISIS. Put this command SR. It accepts. Okay. Same command only. Segment routing MPLS, which you do under ISIS, have to do it on globally. And also, we need to go under the loopback interface. Wait, segment routing MPLS. Here, the global mode, when we say segment routing MPLS, it takes you to the segment routing MPLS mode. Here we need to say connected prefix sig ID map. Address, okay, you go inside here. Address family for IPv4, you are doing this. What is the loopback address? 1.1.1.1/32. Index, you see, you will have two values. Index or absolute. What we are using? Index. You can use absolute and say 16,001. I'm saying index only. 1. Range, you can also say, I may have many sub-routers. We'll talk about this later. Range, I'm going to say only 1. I don't have multiple VRFs, nothing like that. I just got only one control plane. Only one. That's it actually. Okay, that's all. Nothing more to enable. Whatever you learned in the theory only I have done now. So after this, you go again back to the global configuration mode. In here we say the big line. SID map, then address family IPv4, and then the loopback interface IP address with index. Range, you just put 1, okay, as of now. We'll discuss on that later. Only one is node ID you want, that's all. That's the meaning. That's it. Okay, exit. That's all. You need to put this on every node or every device. And then when you see the output, you will be able to see. All right. All right, router 2 configuration is like this. Good. Now what we are going to do is we are going to continue doing our segment routing configuration. Yeah, shall we do that? Let's do it. Okay, we already have a notepad for segment routing. So I'll say open SRSS config. I'm going to paste this just by changing the router ID. I'm going to paste this on every router. Segment routing MPLS, and then go to ISIS, enabling the wide metric, and then enable segment routing. Come back in the global mode, segment routing MPLS mode. You say connect prefixes ID map to that loopback interface IP address, and you give the index value. Index value is 2 for router 2. CSR2. Okay, so this is for CSR2. For CSR1 P router we already did. Now this is for CSR2. Something is wrong. MPLS, no. Oh, I'm in C2. It's not in C2. My bad. Good. I know I didn't impact badly. I need to do it on CSR2, not CE2. Right? And then on CSR3, it's going to be 3, all the rest are same. CSR3. You can see that segment routing MPL is getting enabled. Let me do it on CSR4. And CSR5. Cool. So, what is next? We have enabled ISIS, and then we enabled segment routing globally as well as under the interface. We also need to, let's go and verify and see. I'm in R5, let me say show segment routing MPLS status. It is enabled, cool. And then show MPLS forwarding table for 100, 100, 101. I can see, look at this. I can see the label coming via 2 paths. ECMP. Yep. So what is next? Let me trace route from C1 to C2. Trace route 22, 22, 22, 22. C2. Check the routing. Okay, I don't have route to reach 11. I have all those service provider network, but I don't see the customer route. Maybe there is some issue with CSR1 and C1. Show ISIS neighbor. Okay. I do have a neighbor with GE1. On C1, I think there is something missing. Show IP route IS. See, I don't have any route from C1. Let's meanwhile, because the trace route needs to come out. Meanwhile, I'll go here and try to load C1 configuration and see. Loopback. On loopback, we do have this. We do have ISIS enabled. but let's go wait and see. Let's go once this comes out, we'll go in and see why 11.11.11 is not getting advertised. Meanwhile, I'll go to CSR1 to show you something. Show this network, show route, show IP route. What I want to see is in Excel there is a command actually, detail, where it will show segment routing enabled. Here we don't have such command. No. But we can see in the VPN, show MPLS forwarding. Okay, because we don't have segment routing in this link. It says I will send it to this guy. There is no label for this. There is no local label. There is no SR. If you have a tunnel, then it is possible. When it goes via the tunnel, you will have a label. But we don't have any traffic engineering tunnel as of now. So this command that we saw here, show route, is not from iOS XE, it's from XR. Show ISIS segment routing. Prefix SID map received. What is this? Okay. The global block is, as we already know, it is 16,000 plus 8, which is 23,000. The local SID is 1. And there is a confusion in SID from, okay, I think I have made a mistake, that's why. I have given 2, which is wrong. So let me use a notepad to correct this. Okay, there is a conflict. It's my mistake. Four out of 3, it should have been 3 here. And 4 out of 2, why? Again, I'm doing in C2. It's not in C2. Sorry. CSR2. Yeah, here the index value is looking good. And then CSR4, I'm just redoing it, that's all. And CSR5, okay. Now let's go back and check the command. Good. It shows the global block. I don't know why this command is not working. Fine, what is next? What about the trace? Show IP route. See, there's no route. Show ISIS interface. Show CLNS interfaces. I see CLNS is running on F00 and also on loopback. Show run interface loopback 0. Why this is not getting advertised? Show ISIS neighbor. I do have a neighbor, but nothing is logged. Show ISIS neighbor. Maybe I need to shut down or not shut down. C2 learns the route, but C1 don't. Surprise. Here I'm using 22 wide metric. What about C1? Okay, I didn't put the wide metric command. Show IP route ISIS. Okay, now I got the routes. And now if I check 22, I do have it. Trace. I'm expecting a label. Sorry, for this I don't have a label. We are not running here. So when we have VPN, this will be the source and this will be the destination, then you will have label. But If I trace route from CSR, then we will see the labels. That's what I was actually intended to do. Trace route 101.105 with a source loopback 0. Now you'll definitely see that 16,005 as a label repeatedly used by everyone. See, 16,005 because 5 is the index value I gave. It's the same label everyone uses. Right, along with this, when you put the traffic engineering, you can also ping from C1 to C2 with the labels, which we'll be seeing later. Right now, the packet is going with router 3, the top route. See you in the next following video. Bye.